this is Arika Chaudhary, second year computer science student. Through this video tutorial today, I'll provide you with some background on Moore's voting algorithm. So let me first introduce you all to the problem statement. Given an array A of n elements, find the majority element in the array. Now what is majority element? Any element in an array which appears more than n by 2 times, where n is the size of the array, is called majority element. I hope the problem statement is clear. I'll give two examples to make it clearer. So say we have this array. Here n is equal to 5. So n by 2 will be 5 by 2, that is 2. Now we need to find an element which appears more than twice in this array in order to find out the majority element. So from this array it is clearly evident that 3 is the majority element. Let's take another example. Say we have this array where n is equal to 3. So n by 2, that is 3 by 2 will be 1. Now we need to find an element which appears more than once in an array. So here none of the element appears more than once. Hence our output will be -1. So this problem looks easy, right? Let's start with what comes to our mind very first time, like a brute force solution to solve this problem statement. So what we'll do is have a nested loop, keep a counter for each element in A, keep counting its occurrence. If counter is greater than n by 2, we'll return AI, breaking the loop, else continue the loop. Now it is quite observable that this solution takes O of n square. Why? As it is using a nested loop. A loop inside a loop is called a nested loop. This gives us time complexity of O of n square. And as we are not using any extra space, we'll have space complexity of O of 1. That is a good space complexity, I'll say. So this is a brute force solution. Let's try to optimize it, make it better and explore more. So we have this hash map. What we'll do is we'll create a hash map to store elements and its frequency pair. Then we'll traverse the array from start to end continuously and record the frequency of each element in the array. Then we'll run a loop to find if frequency of any element in the array is greater than n by 2, and if so, we'll return the value, else we'll exit the loop and return -1. Now, space complexity of this algorithm will be O of n, linear space complexity. Why? Because we are using an unordered map. Whereas the time complexity of the solution will be O of 1, as we are traversing the array only once. So until now, we did get a better time complexity, but on the verge of compromising our space complexity, right? So let's now dive into Moore's algorithm to optimize this much better. What I'll do is I'll divide it into two parts, this Moore's algorithm into two parts. First is I'll find the potential candidate element which might be the majority element. Second, I'll check if the selected potential candidate element is a majority element. Okay, so moving ahead, first I'll try to explain you the second half. Please try and understand this. So what we will do is, suppose we have A of res. Res here is the result. So A of result is the element which is potential candidate for majority element. So we need to check for this. We'll initialize a variable count to 0, which will keep a track of occurrence of A result in the array. Now we'll run a loop and count the occurrence of A result. After the loop ends, we'll check if the count is less than n by 2, and if so, we'll return -1. Else, we'll return this A result, that is a majority element. Now let's find out how do we calculate this potential candidate element in the array. We initialize the count with 1, a variable count with 1, and result, which is an index, with 0 initially. We'll assume that A of 0 is the majority element in the array. We are just assuming this. Now we'll run a loop. If the next element to result is same as result, we'll increase the count. Else, we'll decrease the count. And if count while decreasing becomes 0, we'll reset the count to 1 and result to the current index I. So this is what we'll do. When the loop ends, we'll have potential candidate index in the result. Then we'll perform the second half section of the code as I explained in the previous slide. That was to check if this potential candidate is really a majority element. Now let's dry run an example to understand this better. We have this array A which is of size n is equal to 9. What we'll do is we'll initialize the count with 1 and result with 0. We enter the loop. As we enter the loop, I becomes 1, and now we'll check if A result is equal to the current index AI. If it's equal, we'll increment the count. As 3 is equal to 3, we'll increment the count and count now becomes 1. We'll increment I and the elements at index 0 and 2, that is 3 and 4 are not equal. Then we'll decrement the count and now the count becomes 1. We'll increment I again. The element at index 0, that is where result is pointing, and 3 are not equal, that is 3 is not equal to 2. Then we'll deduct the value of count and now the count becomes 0. Now pay attention. This will enter this if loop. When count is 0, what we do? We put value of count is equal to 1 and the result, we'll initialize the result with the current index value, that is I, where that I now right now is 3. We'll continue the loop. I is equal to 4, the element at index 3 where result is pointing right now, and 4 are not equal, that is 2 is not equal to 4. So we again decrement the count to 0. Now count again becomes 0. What we'll do? We'll again set the count to 1 and result to the current value of index, that is 4. Now result is equal to 4. We'll increment a value of I. The elements at index 4 and 5 are same now. Now what we'll do? We'll increment the count and now the count becomes 2. Okay, rest remains same. We'll similarly perform the same algorithm for 6, 7 and 8. Now what we have rest is equal to 4. Finally, we are left with rest is equal to 4. Now we need to check whether this 4 is majority element. How we'll check? Using the step 2. We'll find if 4 appears more than n by 2 times in the array. And if so, we'll declare 4 as a majority element. Now let's look at the code. Add code once. So here's our code. What we'll do is, this is our int main. We'll take input n, what is the size of array, and then we'll input the array using a for loop. Then we are calling some function majority element which takes parameter as a and n. Now let's see what is majority element, and this is printing majority element functions, whatever it is returning. Now let's see what it is. As I've explained you earlier, I have broken down this majority element into 2 parts. First of all, I will check the potential candidate, which can be the majority element, using this half of the code, and the other half I will check if this majority element is really majority in the whole array. So what we'll do is initialize count with 1 and result with 0. And now I'll run a loop. If result is equal to a of I, I'll increment the count, else I'll decrement the count. And while decrementing, if count becomes 0, I'll set count to 1 and result to I, that is the current index. Now at the end of the loop here, I'll have something in result. I'll check now the index which is in result, its element a of result, if it's majority or not. Now again I'll set count to 0. I have a loop. I'll simply increment the count if I find any element which is equal to result. Now after this loop ends, I'll check if count is less than equal to n by 2. If so, it is not a majority element, a result is not a majority element, we'll return -1. Else, we'll return a result. So this is the code, you can have a look through it. Once again, I'll scroll. Okay. So In this algorithm, we need to traverse the array only once. So the time complexity becomes order of n. And since we do not need any extra space like hash map, the space complexity is also constant, that is O of 1. So yes, from O of n square we have come down to O of n, and we need no extra space and hence constant space complexity. So thank you. I hope you'll try to implement this code and implement this algorithm to optimize your solutions. Thank you so much.